bifurcation is actually spread across 2 papers. So
yeah, you just have to say that you're okay with that.
okay, I trust you. Okay, so the title of this talk is, of course, about capturing changes in combinatorial dynamical systems. So I'm actually going to start with a motivating example about what exactly we're hoping to accomplish here, and then we'll go into some of the background and the theory we use to accomplish this. So as a motivating example, I want to consider the Hopf bifurcation. And the Hopf bifurcation is given by this pair of differential equations. Okay, and if you guys are familiar, it is, of course, parameterized by this value lambda. And depending on how the value of lambda changes, the behavior changes. So for this motivating example, we're only going to be interested in the behavior of the differential equation within this 8x8 box. Okay. So when lambda is much less than 0, all we have is an attracting fixed point. Unfortunately, this is smaller than I was hoping, but hopefully you can see that we have an attracting fixed point. Okay, when we raise the value of lambda to be 0, we see the beginning of some periodic behavior. When lambda is greater than 0, we have a periodic attractor. And within the periodic attractor, we have a repelling fixed point. Okay, and as we continue to raise the value of lambda, the radius of the periodic attractor grows and grows and grows. Okay, until the radius is given by the square root of lambda. Okay, until lambda is greater than 16, when the periodic attractor is no longer contained within our area of interest. Okay, maybe these are the only values where our differential equation makes sense, or something like this, right? And then the only solution that's contained entirely within our area of interest is the one where you just stay at the repelling fixed point for infinitely long. Okay, so we have some changes here, right? And notably, we have an attractor that lasts from lambda equals negative infinity to lambda equals 16, some sort of attractor that lasts from lambda equals negative infinity to lambda equals 16, or maybe that persists from lambda equals negative infinity to lambda equals 16. And then we have a repeller that persists onward, right, from lambda equals 0 to lambda equals infinity. So a natural question is if we can use computational topology to automatically detect these sorts of features. And our answer is also ultimately going to be yes by using persistent homology. Okay, so I'm going to give a brief background of persistence. We had a great invited talk on this earlier, but there are some facets that weren't covered very well. And of course, feel free to interrupt if you have any questions. Okay, so I think many of you know that persistence is a tool that is used to capture or summarize the changing homology of filtration. Whenever I use homology, we're assuming we have coefficients from a finite field, usually Z2. Okay, just because that makes homology easier. And we have a nested sequence of subcomplexes. So as an example, consider this complex given by this triangle UVZ, right? We have an associated nested sequence of subcomplexes. And as you move through this filtration, the associated homology changes, right? So at index 0, we have one connected component or one zero-dimensional homology generator. At index 1, we have 2 homology generators in dimension 0. And then at index 2, we go back to 1. And we experience the same sort of thing at index 3 and index 4, where we have the birth white means zero-dimensional generator. And then at index 5, we actually see the birth of a one-dimensional generator, which dies at index 6. Okay. And maybe the key takeaway here is that this barcode summarizes the changing homology, and we can compute it. It's known currently to be computable in matrix multiplication time in the worst case, but sort of an algorithm that is not optimal in the worst case typically computes it in linear time. Okay, so for the most part, it's in linear time. And these bars will be important for summarizing how our dynamical systems are changing. But the tool we're actually going to be using is zigzag persistence, okay, which was not covered in Claudia's talk today. And in zigzag persistence, the inclusions do not have to be unidirectional. Okay, so we're allowed to flip the directions of the inclusions. And like in the previous case, you can capture the changing homology of this sequence. Okay, so as an example, we're going to consider this triple torus, and we're sort of going to consider the darkness filtrations. We're going to start with the darkest simplices and move to the lightest. Okay, so we get, here's an example, right? So when we only consider the darkest simplices, we have a disk, right? Then we get a cylinder, then we have 2 pieces, 2 connected components, each of which have a one-dimensional generator. Here we have 3 one-dimensional generators and so on and so forth, right? So in the same case, the intuition is really the same, right? We can get a barcode that captures the change in homology in the same way we can for the classical resistance case, right? So for the entire duration of our filtration, or our zigzag filtration, we have at least one zero, we have at least one connected component. At various points, we have two, right? For almost the entire generation, we have at least one-dimensional generator. For most of it, we actually have a second, and at some brief points, we have 3 one-dimensional generators, okay? And these barcodes can also be computed in matrix multiplication time with a slight asterisk. Okay, but it's well known how to do this, and we can compute these bars fairly easy. Okay, now I'm going to give a brief review of combinatorial dynamical systems. The tutorial covered it quite well, but it might be good for a refresher. So as a reminder, right, here we're only concerned about simplicial complexes. But a multi-vector, so if K denotes a simplicial complex and less than or equal to denotes the phase relation, then a multi-vector V is a convex subset of K with respect to the phase relation, and a multi-vector field is a partition of K into multi-vectors. Okay, so as a reminder, here we have a simplicial complex, it's the triangle. These bottom 2 multi-vectors are vectors as in the sense of Robin-Foreman, or a discrete Morse theory in the first tutorial. And this multi-vector at the top is a little more complicated, right? Since it includes both the vertex A and the triangle ABC, it necessarily includes the edge AB and AC, because AB is a face of the triangle ABC, and AB contains the vertex A as a face. Okay, so that's what it means to be convex with respect to the face relation. Okay, and here are some more complicated examples of multi-vector fields. I just wanted to highlight that we draw multi-vector fields by drawing a vector from each non-maximal simplex in a multi-vector to each maximal simplex, right? So this edge and this triangle are in the same multi-vector. This edge is not maximal, this triangle is, so we draw an arrow from the edge to the triangle, right? And similarly, this edge and this multi-vector are in the same, sorry, this edge and this triangle are in the same multi-vector, so we draw an arrow between them, okay? Cool. Okay, and right, multi-vector fields on their own are not dynamical systems. So we have to introduce this dynamics generator, as I call it. I believe in the tutorial we use pi, but here I use f. Okay, so if sigma is in K, then the closure of sigma is just sigma together with its faces, right? So the closure of a triangle is the triangle and 3 edges and 3 vertices. And we use this notation bracket sigma to denote the unique multi-vector in the multi-vector field that contains sigma. So remember, a multi-vector field partitions a simplicial complex. So there's always exactly one multi-vector that contains a simplex, and this notation denotes that multi-vector, right? So then we can define the dynamics generator as a multi-valued map, as was introduced in the tutorial, where the image of a simplex is the multi-vector containing the simplex together with its closure. Okay, so what does this mean? This means if we have this multi-vector field on the left, we have 2 multi-vectors. One consists of a vertex, 2 edges, and a triangle. And one consists of 2 vertices and an edge. If we're standing at this edge E, we can go to this vertex on the bottom left because it's a face of E. We can go to this edge on the right because they are in the same multivector. We can go to this triangle because E and the triangle are in the same multivector. And we can actually just stay at E because E is in the same multivector as itself and in its own closure. And for the same reason, we can go to this vertex, right? This vertex is both the face of E and in the same multivector. Okay, so these are the possible moves we can make from standing at that edge E. And this allows us to introduce a notion of a path, right? So a path is just a sequence of vertices or a sequence of simplices that respects this face relation. So we're standing at this vertex in the top right. We can follow this path all the way to this triangle in the middle, which seems to represent an attracting fixed point. It's sort of attracting. It represents an attracting fixed point in a rigorous sense, actually, but the key point is that paths are just sequences that agree with the dynamics chain, okay? Where you're following the rules of how you move in a multi-vector field. And then a solution is just a bi-infinite sequence of such simplices, okay? So here we have one solution. I hope you can see this, where we just stay in this periodic trajectory for infinitely long in the negative and positive directions. That's a solution. Here we have one where we stay in this triangle for infinitely long in the negative direction, and we walk to the periodic orbit for infinitely long in the positive direction. And here we have just, remember each simplex is a fixed point in the dynamics generator, so we can just stay there for infinitely long in the negative and positive directions. Okay, this is a problem that was mentioned in the tutorial, but unfortunately, this doesn't match our intuition from differential equations because every simplex admits a solution, right? Because every simplex is a fixed point, and we don't want this. This doesn't match our intuition. So the way we get around this is using so-called critical multivectors. So you recall from the tutorial that the mouth of A is defined to be the closure of A minus A, right? And multivector is critical if there exists a K such that the relative homology of the closure to the mouth is non-true. So in some dimension, it's non-true. Okay. So as an example, on the top, we have 3 critical multivectors. And on the bottom, we have 3 non-critical multivectors, which we call regular. Okay. So this multivector is given by the closure of the triangle. Its mouth is empty. So the relative homology of the triangle to its mouth is non-trivial in dimension 0. So this is a critical multivector that intuitively corresponds to the notion of an attracting fixed point. Okay. Similarly, here the mouth is in blue. It's these 2 blue vertices. And the relative homology of the closure of the triangle with the mouth is non-trivial in dimension 1. It corresponds intuitively to a saddle. And in this case, the multivector is just the triangle. Its mouth is the boundary of the triangle. So the relative homology is non-trivial in dimension 2. So it corresponds in some sense to a repelling fixed point. Okay. And in each of these 3 cases, it's very easy to check that the relative homology of the closure to the mouth in blue is trivial. So these are just regular multivectors. Okay. And now this lends itself to a notion of an essential solution. And the key idea behind an essential solution is it's exactly the same as a solution, but if you're going to stay in one multivector for infinitely long, in either the negative or positive directions, that multivector must be critical. Okay, so we're allowed to stay in this multivector for infinitely long in the negative direction because it's a critical multivector, right? The relative homology is non-trivial in dimension 2. It represents something like a repelling fixed point. Okay, then we walk to this periodic orbit and we stay there for infinitely long in the positive direction. We're not staying in one multivector, so it's totally fine. We keep moving between multivectors. In this case, we're staying in one multivector for infinitely long in the negative and positive directions, but this is a regular multivector, so that's not allowed. So this is not an essential solution. So this is a special type of solution that better captures our intuition from differential equations. Okay, and we have this notion of invariant set. The way I think of invariant sets is just a union of solutions, okay? The union of simples and solutions, right? So we have one solution here where we spend infinitely long in the negative and positive direction. And we have one solution here where we spend infinitely long in the negative and positive direction. We take the union of those simplices, that gives us an invariant set. Okay. This is different from the intuition that was presented in the tutorial, but I find it easier to think about maybe this way, okay? And similarly, this invariant set is exactly given by one solution. So of course, the union solutions, actually essential solutions, gives us the invariant set. And then this invariant set is much more interesting because this is the union of all solutions where you spend infinitely long at this repelling fixed point in the negative direction, and you walk to the periodic orbit and spend infinitely long there in the positive direction, right? So there are many possible ways to walk from this repelling, to follow a path from this repelling fixed point to this periodic orbit. So if you include all such essential solutions, that gives you this invariant set. Okay? You'll notice you can't get to this yellow triangle from the repelling fixed point. So that's why these are, to this white triangle, that's why these are excluded. Okay. And briefly going to reintroduce isolated invariant sets. As was mentioned by Thomas, we have this technical condition of being V compatible, but that's not very critical for our understanding here. The key point to recognize is that for an isolated invariant set in a closed set N that contains the invariant set, the invariant set is isolated by N if it's not possible to follow a path that starts in the invariant set, stays within the isolating neighborhood, and re-enters the invariant set. So for example, consider this invariant set on the left in yellow, and consider N to be this closed rectangle. It's not possible to start in the yellow, leave the yellow, and re-enter the yellow while remaining in the rectangle. Okay, so because of that, this yellow invariant set is an isolated invariant set, and it's isolated by this rectangle. okay? Whether or not you're an isolated invariant set, you are an isolated invariant set if there exists an isolated neighborhood. So for example, consider this yellow invariant set on the right, and consider the rectangle to be our isolating neighborhood. In this case, it is possible to leave the yellow, stay within the neighborhood, and re-enter the yellow, okay, by following this red path. So that means that this invariant set is not isolated by the rectangle, okay? However, it is isolated by its own closure, okay? It's because this red path is not in the closure of the yellow, okay? So this yellow set is an isolated invariant set, but it's not isolated by the rectangle, only its own closure. And then in the middle, this is an invariant set, but it's not isolated by any neighborhood, right? Because you can always start in the yellow, walk to the red edge, and re-enter the red. So any closed set that contains the yellow will not isolate the invariant set. So it's not isolated, okay? And this is where we diverge a little bit from the tutorial, okay? For isolated invariant sets, we have a notion of an index pair. So an index pair is a pair of closed sets. One is E, it's called the exit set, which is contained in P, that have the following three properties. So they're closed, so they contain all their faces. And we draw E in red, and we draw P minus E in yellow, okay? And you have to have these properties. If you are in the colored simplices, and you want to go to a white simplex, you have to go through the red simplices first, okay? You can't go directly from yellow to white, okay? If you are in the red simplices, you can't go back into the yellow. Okay, so here we notice when we're in the red, we can't go back into the yellow. And then we are an index pair for an isolated invariant set. The isolated invariant set must be the largest isolated invariant set in the goal. So this is a repelling fixed point, okay? It is an isolated invariant set. It's the largest isolated invariant set in the gold. So this is an index pair for this repelling fixed point, okay? And in the tutorial, there's a very special index pair for each isolated invariant set. For each isolated invariant set, you can easily choose an index pair, which is just given by the closure in the mouth, okay? And this was mentioned in the tutorial. Okay. So we can always find an index pair very easily, given an isolated invariant set. But however, index pairs are not unique, right? So here we have three examples of index pairs. You'll notice that we have these properties, right? If you're in the red in any of these, you can't re-enter the yellow. If you're in the yellow, if you want to go to the white, you have to go through the red first. And the largest invariant set in the yellow is this yellow repelling fixed point. So all three of these index pairs are index pairs for the same isolated invariant set. And this was where you get the Conley index. I'm just using the homological Conley index, okay? But if PE is an index pair for A, then the k-dimensional Conley index is given by the relative homology of PD, okay? Or the relative homology of the red and the yellow to the yellow. And it was shown by several people here that this Conley index is well defined, right? So essentially what that means is you take the relative homology in any of these cases, right, of the red and the yellow to the red using Z2 coefficients, we get Z2, right? So I think we showed in the tutorial, if you collapse all of the red to a single point, you get a sphere, right? So in all of these cases, or a two sphere, if you collapse the red to a single point, you get a sphere. So this is what this is captured. Okay, so up to this point, we have a homological invariant, which is associated with isolated invariant sets. We've introduced a means to capture changes in homology, right? So a natural approach is to compute the persistence of this homological invariant, okay? And the first attempt is to just say we're given a sequence of multivector fields, and we can compute an associated isolated invariant set in each of these multivector fields for some, yes, okay, a common isolated invariant set. We can just use the index pair that is obvious, that's not obvious, but the one that we immediately get for free, the closure in the mouth, okay? And we can take the pairwise intersections of this, and this gives us a relative zigzag filtration. And we can compute the persistence corresponding to this relative zigzag filtration, okay? The problem with this, and if we hopefully we would compute the changing Conley index. The problem with this is that the intersection of index pairs is generally not an index pair. So as an example, here are two different index pairs we had earlier for this yellow triangle. If you take the intersection, we don't have the properties we need, right? So it's possible in this case to go directly from the yellow to the white when we take the intersection. And that's illegal. If you want to go from the yellow to the white, you first have to go pass through red. Here you do not have to pass through red. And this has a different relative homology than we would expect. This has 2 generators in dimension 1, not a generator in dimension 2. So if we compute the persistence, we don't get the persistence we expect. Okay, so we need a different approach. And the way we do this is ultimately using what's called an index pair in an isolating neighborhood. In the interest of time, I'm not going to go too in depth into what exactly this is. But the way to think about it is it's an index pair that's in some sense maximal. Okay, in some sense maximal. This isn't a rigorous claim. But the benefit is that we know how to compute these index pairs, these special types of index pairs, okay, using the so-called push forward. But they have a benefit. So first of all, they're index pairs in the sense of index pairs as I originally defined. Okay, but if we have 2 multivector fields over K, then we can define an intersection multivector field by taking a multivector. So say we have V1 and V2, which are multivector fields. We take each multivector in V1, each multivector in V2, we intersect them. That gives us a new multivector field over K. Okay. And if we have P1 and E1 and P2 and E2, which are index pairs in N under these multivector fields, then the intersection pair is always an index pair in N under this intersection multivector field. Okay, so let me show you what this means. Right, on the left we have an index pair in N. On the right we have an index pair in N. And what's changed here, these multivector fields on the left and the right are very similar. All that's happened is that this vertex or this vector which is pointing up on the left is pointing down on the right. Okay, that's all that's changed in the multivector field. So when you take the intersection of the index pairs, okay, we get this pair in the middle, and it corresponds to the intersection of the multivector fields, or it's plotted over the intersection of the multivector fields, right? So instead of having a down arrow or an up arrow, we just have 3 singletons. Okay, and in this case, the relative homology is what we would expect, right? In each case, the relative homology is non-trivial in dimension 2, and when you compute the persistence, we get what we want, right? We have a 2-dimensional bar that persists all the way through. Okay, so this is one of our main results from the first paper, and this gives a natural strategy. So we've basically you fix N, and for each multivector field, you compute the maximal invariant set in N and corresponding index pairs, convert those into index pairs in N, and compute the zigzag persistence, and we get the persistence of the common index. Okay. So on our motivating example of the Hopf bifurcation, right, I use the same plotting system where P minus E is in yellow and E is in red. We get what we would expect. Okay. So as we raise the value of lambda, the radius of our periodic orbit increases. Okay. And the maximal invariant set in N is given by the repelling fixed point, the periodic orbit, and all connections between them. Okay, so the maximal invariant set is just a big attractor, convex attractor, and it remains a convex attractor until part of the periodic orbit exits Rn, and then all we're left with is the repelling fixed point. Okay. So when you actually do this, we get what we would expect, right? We have a 0-dimensional bar that represents the presence of the attractor that lasts up until lambda equals 16. And then we have a 2-dimensional bar that represents the presence of the repelling fixed point, which lasts up to lambda as far as you want it to go. Okay, cool. How am I doing on time? I'll briefly mention that there's a slight problem with this, and that this approach isn't very resilient to noise. So these on the left and the right are 2 index pairs with the same situation, right? All we do is we flip this vector that's pointing up to pointing down. And if you take these index pairs in N and take the intersection, then the relative homology here in the middle has 2 generators in dimension 2. Okay, not 1 generator in dimension 2. So what's happening here is we have a breaking of the bars, right? What we want is we want 1 bar to persist all the way through. But here, instead we have 1 bar that dies in this multivector field, another bar that's born in this multivector field. Okay, and this isn't the intuition. So it turns out a way to do this is we can expand P minus E, or reduce the size of E. E is in red. And this is one of the results, is that basically you can remove regular multivectors from E. And this lends itself to a natural algorithm that gets us some noise resilience. So here's a closer up view of this happening in practice on our discretized version. And when you, not coming through pretty, but what you shrink the size of E, grow the size of the yellow region, and when you compute the persistence, you get the persistence you would expect. Okay. Right, and we showed that when you shrink the size of E, you still have an index pair. Okay. Okay, so now I'm going to move actually into talking about a slight deficiency in the previous approach. I'm going to consider another motivating example. Okay, so this motivating example is a little bit more complicated, and there was a similar one in the tutorial today. But initially, it's hard to see. We have a repelling fixed point in the center, and we have a periodic attractor that surrounds the repelling fixed point. Okay, and what happens is we see a bifurcation where the repelling fixed point splits into a periodic repeller and an attracting fixed point. So on the inside, it's kind of the opposite of the Haas bifurcation. A repelling fixed point bifurcates into a periodic orbit and an attracting fixed point. And the size of the periodic orbit grows and grows and grows, or the periodic repeller grows and grows and grows until it collides with the periodic attractor. And this is, again, hard to see, but we now have it's called a semi-stable limit cycle. Okay, so the discretized version of this looks like this, right? Initially, we have a repelling fixed point and a periodic attractor. The repelling fixed point splits into a periodic repeller and an attracting fixed point. And then eventually the periodic repeller and the periodic attractor collide, and you have a semi-stable limit cycle. It's attracting on the outside, repelling on the inside. Okay, so we have two bifurcations here, right? A split and a merge. Okay, but the problem, so if you use the algorithm I just presented, and you always take the maximal invariant set, the maximal invariant set here is actually always exactly the same, right? Because while we see two bifurcations, the maximal invariant set is always given by everything within this rectangle. Okay. So this is problematic because even though we have some rich behavior, we're not capturing it with the previous method, right? And in this paper, we presented, well, you also briefly mentioned you can choose different invariant sets. Maybe you don't choose the entire rectangle, but you're still losing a lot of behavior. So here, if we compute the persistence of, say, the periodic attractor to the semi-stable limit cycle, you're only getting a small slice of the picture. Right, you're missing out on the initial bifurcation. Okay, the semi-stable limit cycle has trivial common index. This is why the bars don't go this through. So we need some new approach, not only to capture the persistence of the Conley index of maximal invariant sets, but to compute the persistence of the Conley index within invariant sets. Okay, and the way we do this is by computing the persistence of the so-called Conley-Morse graph, okay, which was also introduced in the tutorial. Maybe I'll just, for our purposes, we can think of a Morse decomposition of an isolated invariant set as a decomposition into smaller isolated invariant sets and the connections between them. Okay, I'm omitting some technical details here, right? But here we have an isolated invariant set, right? We can decompose this isolated invariant set into this repelling fixed point, this periodic attractor, and the connections between them. Okay, and this gives us a graph, right, where we have yellow representing the repelling fixed point and blue representing the periodic attractor. And I hope you remember these are the Poincare polynomials, right? So t squared represents that there's one generator in dimension 2, right, in the relative homology here. 1 plus t represents there's one generator in dimension 0 and one generator in dimension 1. Okay, so perhaps the intuition now is that if we are given, or if we have our three multi-vector fields and our three Morse decompositions, and we can compute the persistence of the Conley-Morse graphs, then we'll be computing the persistence of two things. One is the structure of the graph, right? And another would be how the Conley index changes across the various nodes in the graph, or the various vertices in the graph. However, if you look at every possible change, there are many, right? So if you have n Morse sets in each graph, you have n graphs, then you have like n to the n possible ways you can change, right? So we want to drastically reduce that, right? And it seems pretty intuitive that we should be able to, okay? Because somehow, naturally, you can only persist from this repelling fixed point to this periodic repeller, or from this repelling fixed point to this attracting fixed point. It doesn't make any sense to look at the persistence from this repelling fixed point to this periodic attracting, right? They're not really connected in any way. Okay. So ultimately, what we are going to obtain is two types of filtrations, which we have dubbed graph filtrations and Conley-Morse filtrations. Graph filtrations capture the changing structure of the graph, which isn't so interesting. So I'm going to be focusing on Conley-Morse filtrations. And ultimately, what we do is, so each of these nodes corresponds to a Morse set, right? So we fix an index pair for each Morse set, okay? And then you can only get, so let's say this Morse set has index pair P1, E1, and this Morse set has index pair P2, E2. You can only get persistence from this Morse set to this Morse set if P1 minus E1 intersects P2 minus E2 is non-empty. If the intersection is empty, persistence is impossible, right? Nothing can persist onward. So it's natural to only look at those sequences of Morse sets for which you have consecutive non-empty intersections, okay? So we follow such maximal sequences across the Conley-Morse graphs with non-trivial intersection, okay? And that, so here there are several multivectors in between each of these stages, right? There are multivector fields between each of these stages. We're not going directly from here to here to here, okay? And when we look at this in practice, right, you get what you would expect, right? You have some intersection initially between the repelling fixed point and the periodic repeller, and from the periodic repeller and the semi-stable limit cycle, okay? Similarly, we have the repelling fixed point turning into the attracting fixed point, which is this one, and we have the periodic attractor turning into the semi-stable limit cycle. So we've reduced this to just 3 sets of filtrations, okay? And we can use the previous approach to compute the persistence across these 3 filtrations and just look at the barcodes, okay? So here I have drawn exactly this. We have the repelling fixed point, the periodic repeller, and the semi-stable limit cycle. When you compute the persistence, we get a 2-dimensional bar that persists through. And the 2-dimensional bar is born with the repelling fixed point and persists through the periodic repeller, okay? The 1-dimensional bar is born when the repelling fixed point becomes a periodic repeller. So this birth of this 1-dimensional bar indicates this bifurcation, okay? When we go from being a repelling fixed point to a periodic repeller. This 2-dimensional bar captures the repellingness that is preserved, okay? The problem is when you look at the persistence associated with the fixed points, okay, you get a 2-dimensional bar here, which represents the repelling fixed point, and then it just becomes a 0-dimensional bar that becomes an attracting fixed point, okay? This 2-dimensional bar is already captured here, right? This 2-dimensional bar captures the repelling fixed point turning into the periodic repeller. This 2-dimensional bar just captures the repelling fixed point. So it's strictly redundant, okay? So we have an algorithm that removes such redundancies. And ultimately, when you look at the barcodes removing the redundancies, we get a very nice set, right? So we have a 0-dimensional and 1-dimensional bar that represent the periodic attractor. We have a 0-dimensional bar that represents the attracting fixed point. We have a 2-dimensional bar that represents the repelling fixed point and the periodic repeller. And this 1-dimensional bar indicates the birth of the periodic repeller, okay? And then our graph just has one connected component, which is a little more boring, right? But ultimately, this gives us a barcode to compute changes at a much finer granularity than our initial Conley index persistence approach. Okay, so I'm just going to conclude and give some directions for future work. So in this presentation, we've devised 2 ways to capture changes in combinatorial dynamical systems, but there are sort of 2 major questions that remain unresolved, right? So one was that, and which was mentioned in the tutorial, was that in this discretization, we just assumed that our discretization was nice, and it happened to be nice, right? I don't know any details about how we discretized, but it seemed to work out nice. It reflected our intuition. Okay. It would be nice to have some sort of rigorous result about discretizations. Like if you discretize, a differential equation that has this sort of structure, then we would expect to see the same thing in the combinatorial setting. And then there are questions about stability, right? And Mihao will be talking in the next session about an approach that's somewhat adjacent to stability, but it's not quite stability in the sense of persistence, for example. And here are my references. So thank you. Right. Other questions, comments? Cool. Thanks.
Question was very clear.
Thank you.
Now we have the breakout discussions.